Thank you for the introduction. The title's different from the advertised one, but the content's the same. There's two questions. If I have my glasses, I can read them. The first question is, will artificial intelligence soon be smarter than us? And for a long time, for like 50 years, I was working on trying to make artificial neural nets in order to understand how the real brain might work. And I always assumed that the real brain was better and the artificial neural nets were worse. And if you made them more like the brain, they work better. And a few months ago, I suddenly changed my mind. And that's why I decided to leave Google and talk about the risks. And the risks, obviously, will people be able to stay in control if you get super intelligent things? Because there's no examples of a more intelligent thing being controlled by a less intelligent thing since Biden won the election. I'm going to make a few speculations about that, but the main content of the talk is just going to be about the reason why I think these things are going to get more intelligent than us. So the first question. I don't know much about risk. I talked to a whole bunch of risk people today who knew much more than me, so I won't talk about that. So in conventional computing, you use computers that are designed to follow instructions. And the fundamental property of a computer is that you can run the same program on different pieces of hardware. And so the knowledge in the program is immortal in the sense that if a piece of hardware dies, the knowledge doesn't die. You can run it on another piece of hardware. To do that, you need to run transistors at very high power so they behave in a reliable digital way. And you can't make use of the analog properties, the analog and highly variable properties of a particular piece of hardware, because then you wouldn't be able to do the same thing on a different piece of hardware. So I got interested because of the very high power used by these large language models, the big energy consumption. I got interested in whether there was a much cheaper way to do computation in terms of power that we could use now and we couldn't use previously. And digital computers were designed to be programmed by people, which is why they had to follow instructions precisely. But now we know a different way to make general purpose computers do particular tasks, which is learn from examples. And if they learn from examples, maybe we can get rid of this basic principle of computer science, which is you have to separate the software from the hardware. Maybe we can use analog computers that make use of all these analog properties and aren't reproducible. So you just can't transfer the knowledge to another computer, but you can run at very low power, like 30 watts. So obviously there's big advantages to separating software from hardware. You can write one program and it'll run on all your iPhones. It also means you can have a separate department where you don't know anything about electrical engineering and you call yourself computer science. If it's all mixed up together, you can't do that. And so when you don't separate the software from the hardware, you get what I call mortal computation. That is, you're going to learn in the hardware, and what you learn is only going to be any good for that particular piece of hardware because you're making use of all its weird analog properties. Now that's great because we can use low power analog computation and we can maybe grow hardware in 3D where we don't know the connectivity or the precise properties of the individual neurons if it's neural net-like hardware. But we've obviously got one big problem, which is we're going to have a learning procedure that can learn in this hardware without knowing the exact properties of the hardware. And I'll talk a bit about how you might do that. It's probably not going to be backpropagation, because in backpropagation, you have a forward pass through layers or through time, and you have to know the properties of the forward pass in order to use backpropagation to get gradients. If you don't actually know the properties of the hardware, you need a different kind of learning algorithm. So advantages of mortal computation, you can use weight level parallelism. So you can have trillion-way parallelism. And that means your computing elements don't need to be very fast. That's what the brain does. And we can use hugely less energy, and we can grow the hardware. Now, it might be good not to start again from scratch. I was guessing that we would end up actually re-engineering biological neurons as the hardware. But as you'll see, we may not have time for that. So I just want to give you one example of a computation that's obviously much more sensibly done analog than digital. So suppose you want to multiply a vector of neural activities by a matrix of weights. And that's what we want to do all the time. That's the main computation we do. So you could drive transistors at very high power and represent the activities as digital numbers, and then perform a whole bunch of operations on the bits to multiply them together. Or you could make the neural activities just be voltages, and you can make the weights be conductances. And there's physicists around, so I hope I got the units right. If you multiply voltage by a conductance, I think you get a charge per unit time. And charges add themselves up. So now you can multiply a vector by a matrix very simply without ever representing anything digitally. And it's very efficient. There are chips around that do that now. The problem they have is then they try and digitize things afterwards before they do anything else with it. But this particular computation can be done efficiently. So the other big, I'll get back to the learning problem in a minute. The other big problem for mortal computation is that hardware dies and then everything it knows gets lost. And so the solution to that problem in mortal computation, there's a completely different solution in digital computation, but in mortal computation, the solution is the teacher tries to distill the knowledge into a student. And the way you do that is the teacher shows the student the correct responses to some input, and the student tries to mimic those responses. And that's what was going on with Trump's tweets. Left-wing people kept complaining that all the things he said were false. That was completely irrelevant. That wasn't the point. The point was you take a situation and you show people how to react to it, and your followers try and react like that. And it turns out that's much more effective than reasoning with people. So that's how distillation works for distilling prejudice. So let's think about an agent that's classifying images into 1,024 categories. If you just tell the agent the right answer, you're only giving them 10 bits of information. So you're only constraining the weights by 10 bits when you say you should give this class for this input. But suppose you already had a teacher who was trained. The teacher will give probabilities for all the outputs. And that's 1,023 real numbers because they add up to 1. And as long as those probabilities aren't too small, if you train a student to mimic a teacher, each training example is far more valuable because the student is trying not just to get the right answer be the most probable thing, assuming the teacher got it right. The student's trying to match the probabilities of the teacher for all the other training examples. And actually, in many cases, there's much more information in the relative probabilities of wrong answers than there is in the right answer. So for example, if I show you a BMW, the system will say sort of 0.8 is a BMW and 0.1 it's an Audi, and there's a 1 in a million chance that it's a garbage truck. There's no German manufacturers here, no. There's 1 in a million chance it's a garbage truck, but the point is, it'll also say there's a 1 in a billion chance that it's a carrot. And if you look at all the things that get a 1 in a million chance, they're other vehicles. So it's telling you a lot about the classes of things by all the things that get low but not totally zero probabilities. And vegetables is not, and so they get very much smaller probabilities. And that ratio between the garbage truck and the carrot is telling you a whole lot. So training a student to mimic the probabilities of a teacher is good, especially if the probabilities aren't too small. And we can make the probabilities not too small by using a high temperature. So normally, if you have multiple alternative outputs, you use the softmax, which is, you say, the probability of each answer is proportional to e to the logit for that answer, where the logit is the amount of evidence you got for that answer. If you just scale that by temperature, you get much softer probabilities. And so I've got an example of that where it may surprise some of you to know I use the MNIST digits. And I've got a good teacher, and then I've scaled down the probabilities so they're much softer. And if you look at this, these are all 2s. But if you look at that middle row, the teacher thought, yes, it's a 2, but it's just slightly like a 0. It's much more like a 0 than any of the other 2s. And so you can see on that one training example, you're teaching the system things about zeros as well by saying this is a 2 that looks a bit like a 0. Or if you look at the second row, that's a 2 that looks a bit like an 8. And that's very useful extra information. So the reason I'm talking about distillation quite a lot is because that's how we get knowledge between ourselves. It's also how you get knowledge between one digital system and a different neural network that's got a completely different architecture. So often you want to train a great big model and then get that knowledge into a smaller model, and you use distillation for that. And one nice thing about distillation is when you're training the student from a teacher and training the student to get the same probabilities for wrong answers as the teacher, you're actually training the student to generalize the same way as the teacher. So it's one of the very rare cases where you're actually training the student on how to generalize. Normally you just train it to get the right answer and hope it'll get the right answer in other cases. But here we're actually training it to generalize. And obviously a single label isn't a very rich answer. So you'd be better off training the student by giving it an image and then giving it a great long caption for the image and training it to predict all the words in the caption. And that way you can get more information per training case. So that makes distillation work better. So that's how distillation is, how you get information between 2 analog systems. And that's what we were doing then. You've got a very old analog system here, and you've got a few old ones and a lot of young analog systems there. And we're trying to get information from this old analog system into these young analog systems. And the whole point of this talk is that process isn't very efficient, as I just demonstrated. It's a slow and painful process. We can't get, wouldn't it be great if I could just sort of go chunk and everything I knew went into your brain? That would be so good. Wouldn't be much good for the university, but it would be, yeah. But that's what biological systems have to do. Now let's talk a bit about the learning algorithm, because this is what, thinking about this was one of the things that made me change my mind about which is better, digital systems or biological systems. So if you don't want to backpropagate because you don't actually know what the hardware is doing, you can use a simple algorithm which is got an evolutionary flavor, which is you generate a small random perturbation to the weights, and you have some global objective function. You put some examples through, and you see whether you do better or worse on this objective function after you've made the perturbation, and then you take a step in the direction of the perturbation that's proportional to how much better you did. And the thing about that is, on average, it's going in the right direction. If you do it enough times, you'll go in the same direction as backpropagation, but it's got very high variance. So it'll only work in very small systems. Also, if you use the same weight perturbation for everything in a mini batch of examples, you get even worse variance. And if you use different weight perturbations, you can't use matrix multiplies, but that's just for insiders. It's much better to use activity perturbation, where you perturb the input to a neuron, and you do the same thing. We perturb the inputs to all the neurons, so they get the inputs they're getting from the rest of the net, plus this additional perturbation. And then you see how much better you get as a result of that perturbation, and take a step in that direction proportional to how much better you got. And obviously, there's far fewer neurons than there are weights, so it's got much less variance. And that's good enough to learn problems like MNIST. It learns slower than backpropagation, but it learns at a reasonable speed. The problem is, once you start trying to scale that to big nets, it's just hopeless. You can learn things like MNIST, you can learn things like CFAR10 if you're very determined, but ImageNet, where you have millions of images or 1 million images, is just much too slow.